Okay. Hello, everyone. Today, I'm going to present a paper published in Michael this year, and the title is AutoFL, Enabling Heterogeneity-Aware, Energy-Efficient Federated Learning. And this is the outline. Firstly, I will show you the backgrounds of federated learning over mobile devices training. Next, I will show you the motivations and the observations found in this paper. And the third part is the algorithm proposed in this paper called AutoFL, a reinforcement learning design. Finally, I will conclude this paper with the performance evaluation. As we all know, federated learning is a distributed learning framework which can collaborate lots of mobile devices to train a unified global model. It has some interesting applications like the Google Gboard. It can also has the potential to support some healthy related or financial related applications in the future. However, there are still some challenges during the federated learning training. And the first one is the system heterogeneity. There are lots of different compute resources of the mobile devices, like the CPU, GPU, and DSP. So the high degree of system heterogeneity introduces varying, potentially large performance gaps across smartphones in federated learning. And the second challenge is stochastic runtime variance. The mobile execution is stochastic by nature. So when we train the federated learning models, there may exist other co-running applications and the signal strength is changing. And all of this leads to the struggler problem. And the third one is the data heterogeneity. We cannot always have the IID data. Sometimes we may have the non-IID data. So such non-IID data may defer the convergence. Beyond the challenges mentioned above, energy efficiency is another important component in federated learning training because most of the phones are powered by the battery. So the energy efficiency federated learning can enable on-device training anytime with better model quality and user experience. Therefore, for this paper, their goal is to design an energy optimization framework called AutoFL, where they do two things. One is the user selection. They want to select key participants in all available devices. And the second one is execution target selection, where we need to determine where can we run our program in CPU, in GPU, or DSP. At the same time, they consider the system heterogeneity, the stochastic runtime variance, the data heterogeneity during the training. And for this energy minimization problem, it's difficult to solve it by the optimization method because the optimization decision varies with lots of components like the neural network characteristics, the federated learning global parameters, the device or data heterogeneity. Moreover, some components like the device or data heterogeneity are always changing over the time. So the design space is massive and infeasible to emulate. Therefore, in this paper, they use a reinforcement learning-based approach. They want the machine to learn and make the decisions automatically, and we call it AutoFL. Next, let's see the motivation of this paper and some observations found here. Firstly, they simulate a realistic federated learning execution environment with 200 devices. And first of all, they simulate the system heterogeneity, where they have three types of the devices: the high-end device, the mid-end device, and the low-end devices. For high-end devices, which means they occupy the powerful CPU or GPU, and for mid-end device, maybe they occupy the common CPU or GPU. Therefore, the training time performance varies amongst the devices. Secondly, they simulate the stochastic runtime variance. The computing and communication is highly dynamic. For example, for this high-end device 0, if the signal strength is poor, the communication time will increase. And for this device 1, if there are some other co-running apps, the computing time will increase. So the computing and communication is highly dynamic during the training. And thirdly, they simulate the data heterogeneity, where they consider the non-IID data during the training. Both based on these 3 components, there is a massive optimization space for the federated learning training. Next, let's look at some observations found in this paper. The first one is the impact of federated learning global parameters and the neural network characteristics. And here we have the conclusion that the optimal cluster of participating devices will depend on these federated learning global parameters and the neural network models. And here we consider 8 cluster settings of devices. C1 means we have 20 high-end devices, and C7 means we have 20 low-end devices. Let's take the CNN model on MNIST dataset as an example. And we consider 4 global parameter settings here. B here is the batch size, E here is the local training epochs, and the key here is the number of participants. And the simulation results are shown here. PPW means the performance per watt. It can represent the energy efficiency. And from this figure, we can find that for each site, for different settings, we have different optimal clusters. For example, for S1 setting, the optimal cluster is C1, and for S2 setting, the optimal cluster is C2. So from this figure, we can observe that if when the computation load is larger, means this S1 setting, both the batch size and the local training epochs is large, and in this setting, including more high-end device is beneficial for the energy efficiency because the optimal cluster is C1 cluster. And when the computing loads decrease, which means from setting S1 setting to S2 setting as S3 setting, including more mid-end or low-end device is more beneficial for the energy efficiency. And the reason is that the mid-end or low-end device in S2 and S3 is more energy efficiency since their lower power consumption amortize the performance gap reduced due to the lower computation and memory requirement. And also the authors take the experiments on this LSTM model and the Shakespeare dataset, and they found that the energy efficiency for such model of mid or low-end device is comparable to high-end device. The reason is that for this LSTM model, they don't have the convolutional layers. Thus, we don't need the powerful CPU or GPU. Therefore, the performance of mid or low-end device is comparable to the high-end devices. So this is their first observation.
So Dan here, so you mean the performance per watt is when the learning achieve convergence, right?
Yes,
we do the calculation.
Yes, we can calculate the flops and we can calculate the watt, and we have this PPW.
Okay, so they run both CNN on MNIST and LSTM on Shakespeare, right?
Yes.
Okay, so what they mean is it doesn't matter what kind of model and data set, they can achieve similar conclusion.
No, for example, for the CNN model, if the computing load is large, we prefer to some high-end device for the yes. For the computing loads decrease, we prefer to include more low-end or mid-end device in the CNN model. But in this LSTM model, it doesn't matter. for both these all of these type of devices, they have the similar performance.
You mentioned why is that? I missed that part.
For example, for this one, because they don't have the convolutional layers, so
okay.
we don't need the powerful GPU. So that's why the performance of the mid or low end device is comparable to high end device.
Okay, so that means LSTM on Shakespeare is more CPU intensive. GPU is okay, right? So for CNN model, it's more kind of a CPU, both CPU and GPU intensive.
Yes,
like
yes.
That, right? Oh,
yes.
Okay, thank you.
Okay, let's move to the next page. For their second observation, the impact of runtime variance. And here we have the conclusion that the optimal cluster of participants significantly varies along with the runtime variance. We still consider this CNN and MNIST model, and we still consider these 8 sightings. And we consider this problem in 3 scenarios, which means the first scenario is no runtime variance, and the second scenario is there exists on-device interference, and the second scenario is the network is not stable. And we have 2 conclusions. And for example, for this no runtime variance scenario, the optimal cluster is C3. But if there exists some on-device interference, the optimal cluster is C1, which means we prefer to high-end device in this setting because the high-end device has the high computation and memory capacities to handle the interference. But when the network is not stable, we prefer to low-end devices because in this case, the communication is dominant. So the impact of performance gap among different categories of devices decreases along with the decreased portion of computing time. So in this scenario, we prefer to low-end devices. And this is their second observation, the impact.
Here, I have another question. What do you mean by on-device interference?
Which means we have some other applications running on the device.
You have
there are some other yes, like the web browsing and playing some other games, etc.
So they work on which kind of a test bed?
The Amazon EC2, a virtually cloud platform.
Okay. So, but Amazon EC2 is still kind of a model, right? It's not. I know they're doing well, but it's still they're kind of a model. It's a virtual model instead of a real device, right?
Yes, it's not a real device. So they run the federated learning on that model, and they measure the energy consumption with 3 devices. I will show it in the performance evaluation part.
So the real device shows similar features and characteristics, right? That's what
yes.
Okay.
Yes. Okay, let's move to the third observation, the impact of data heterogeneity. Here, the participant selection strategies that ignore data heterogeneity will lead to the suboptimal federated learning execution. And this is obvious with the increasing of the non-ID level, the final accuracy will decrease, and also we need more aggregation runs. Non-ID M% here means M% of K participant devices have non-ID data. So they consider the data heterogeneity during their training. Next, let's move to the algorithm they proposed called AutoFL, a reinforcement learning based design. And this is the framework of their proposed approach. It is a reinforcement learning approach. Their goal is to minimize the energy consumption and maximize the convergence speed. So the reward here can be defined related to the energy and accuracy. And for the action, it includes 2 parts. One is the user selection, where we want to choose key participants in all available devices. And the other one is execution target selection, where we need to choose CPU, GPU, or DSP. And in this paper, we consider all of these system and data heterogeneity and stochastic runtime variance features. So all of these components can be considered as the state in the federated learning. And so this is the overall framework of their proposed method. And for their method, it has 3 advantages. The first one is better performance, which means they can significantly improve the energy efficiency and the convergence speed. And the second one is low training and inference overhead, because they use the Q-learning algorithm, a very simple and easy reinforcement learning algorithm. So the training and the inference overhead is low. And the second one is the scalability. They can share the Q table among the same type of devices. Therefore, it can support a lot of devices, and it has a better scalability. Next, let's see the details
I have
of
a quick question. So for the available processor selection, what do they mean? They mean because some of the job need both CPU and GPU, right? Some of them CPU intensive, but they still need a GPU, right? You know what I mean?
Yes,
some of them is kind of GPU intensive, but they're kind of need a CPU too.
Yes, but in this paper, I think they assume that they can only perform the execution in one of these 3 compute resources, either CPU, GPU, or DSP.
Oh, is that possible? I'm not a hardware guy, but
I'm not sure, but they have these assumptions.
Okay, if it's in micro, supposedly those hardware guy, you know, I don't know, probably they think this is right, but
yes.
For example, if you are given task, if you only perform with the GPU, CPU, okay, for example, even the task is a CPU intensive. So is that possible if you jointly use the CPU and GPU? I mean, it will be more energy efficient, or running time will be faster or something. Is that possible? Did they discuss something like this?
No, they don't discuss these things.
Okay.
Yes, I'm not sure actually.
Okay.
Yes. Because they only have these simple settings for the simulation, and they don't have too much theoretical analysis on this.
But not theoretical analysis. I mean, even for, do they have a real world test bed, or they only run the simulation?
They only have the simulation. Yes. Okay. Maybe in that virtually cloud computing platform, we can easily choose CPU, GPU, or DSP. We can easily simulate that. Yeah. Yes.
But if you put that on the real mobile device, I'm not sure though. Can you, from a software point of view, you can make the selection of the CPU, GPU, or something? Can we do that?
I think from my experience, if we choose the CPU, maybe we don't need the help of the GPU. But if we choose the GPU, maybe we still need the help of the CPU for some memory access or some other things. Yes.
Yeah, that's exactly what I think. I think it's not, I mean, if you run it on the simulator on EC2, probably that's true. But if you want these things to deploy on the real world mobile device, probably there's some small gap. Yeah.
Yes.
Okay.
Let's move on. Let's turn to the detail of their model. Firstly, let's look at the state. It can be defined as the components related to the energy efficient federated learning execution. And here we summarize the state features of this AutoFL model. It contains the neural network related features like the number of convolutional layers, the number of fully connected layers, and the number of recurrent layers of the neural network model. It contains the global parameters like the batch size, the number of local training epochs, and the number of participant devices. It also considers the runtime variance like the CPU utilization or memory usage of co-running apps and the network bandwidth. Besides, they also consider the data heterogeneity, which means they also consider the number of data classes for each round. So this is their state space. It should be noticed that the state space is discrete, which means each feature can be divided into several categories to reduce the complexity of their algorithm. So this is a definition of the state space. Next, let's move to the action space. In their paper, they have two types of the actions. One is the global level action, where we can select the participants to, the first one is the selection of participant devices. We need to choose a K device to participate the training among all unavailable devices. And the second level is the local level, where we need to choose the execution targets, either the GPU, CPU, or DSP. And also, if we choose the CPU or GPU, we can further consider the BVFS settings. And next is the reward function here. So for the reward function, it includes three parts: the local energy consumption, the global energy consumption, and the accuracy. Local energy consumption means the energy consumption for each device, and the global energy consumption means the energy consumption for all of the devices in the system. Next, let's first look at how to calculate the energy consumption. And in this paper, they consider two parts: the computing part and the communication part. So if the execution target is the CPU, the energy consumption can be calculated as the sum of all cores' energy consumption. And for each core, it includes the busy state and the idle state. And if the execution target is GPU, the energy consumption can also be calculated as the sum of the busy state and the idle state. On the other side, for these DSP settings, we have the similar equations to calculate the energy consumption. And so this is the computing part. And for the communication part, if the device is selected, it can be calculated as the transmit power times the transmit time. And if the device is not selected, we have this ideal energy consumption. It equals to the ideal power times the time consumption in each round. So this is the communication part. And for this energy consumption, if we have these two parts, we can calculate the local energy consumption as shown here. If the device is selected, the local energy consumption can be computed as the sum of the computing energy plus the communication energy. Otherwise, it only includes the idle energy consumption. And the global energy consumption can be calculated as the sum of all the local energy consumption. And if we have this energy consumption function, we will have our reward function. It will be defined here. If the accuracy is not increased compared with the previous round, so the reward can be defined as the current accuracy minus the 100. It should be a negative value. Otherwise, if the accuracy is increasing compared with the previous round, it can be defined as the minus of the global energy minus the local energy plus the accuracy of this round and plus the accuracy improvement. So this is the definition of their reward function, and it considers both the energy consumption and the accuracy improvement. And this is a reward.
I have a quick question. So first of all, the accuracy is what kind of what kind of accuracy? You're pointing
It's a global
to fair learning,
the
right?
global, yes, that's the global accuracy of the federated learning.
Okay, so training or testing.
They didn't say it's training or test. I think both of them are okay for this scenario. I think they didn't say it's training or test.
Okay, it's definitely it's not like the training loss or something, right? It's just
yes.
It's not a training loss, right? But
it's not the training loss, the accuracy.
It's accuracy.
Yes.
Right. The second thing is where is the 100s the number comes from?
For example, the accuracy should be 80, 70, or 90, and because we want to maximize the reward, so if the accuracy is not increased, we should define a negative value. So that's why they define the gap between the current accuracy and the ideal accuracy, the 100%. I think it just want to represent the 100% if the model is converged ideally.
Oh, in other words, it's one, right? But even
yes.
If one, because we know the accuracy never achieve one, right? So why they choose? Because if it's a specific number, it's always weird.
Yes, but
okay. Well, I can accept that for reinforcement learning. It's fine. But I want to say it's a detailed relationship in terms of energy and the state. So how can they connect them? Yes.
The energy and the state.
Yeah, because you list so many states, right? It's a state. Okay, action. Okay, one state to another state. Okay, yeah. But yeah, what I mean is, how can you put all the states information together? Okay, you just list those state information, right? You give a very, very complex graph.
Yes, for the state, since we only need these correct values, so it is not complex to represent the state.
Okay. Oh, you give a range for all this number. Okay.
Yes.
Okay, you can list a not so difficult graph. Okay. Thanks.
Okay. Next, let's move to the implementation detail of their algorithm. Yes, here, since both the state space and the action space are discrete, therefore they use a very simple Q-learning algorithm. And the main idea of the Q-learning is that we maintain a Q table. So this is a Q table. The row index is the state, and the column index is action. And according to this Q table, for each state, we need to choose the largest action. We need to choose the largest Q value, and then we can make the decision of the action. And let's see the implementation detail of their algorithm. And for each round, we firstly use the epsilon greedy policy to choose the action. Epsilon greedy policy means with the probability epsilon, we select the actions randomly, and otherwise we will select the action according to this Q table. Since it contains two levels, from the local level, we will choose the execution target with the largest Q value. For example, if the state is here, we need A1 is the CPU, A2 is the GPU, or A3 is the DSP. And then we will choose one with the largest Q value. This is a selection of our execution target. And the second level is a global level. After we select the execution target, we will sort all devices by their Q value and choose the top K devices to participate in the training. So this is their epsilon greedy policy. And after we have this, after we have the action, we will execute the training according to that action. And then we will store these transactions in the memory. For each state, we can choose one action, and we will have our reward. And the state information will move to the next step. And finally, we can update our Q value according to this equation based on the transaction stored in the memory. So, and we can repeat these steps until the model converge. And this is a training detail of their AutoFL method.
I have another question. So there's going to be two Q table, right? One is Q table like state locally and action, and another is state global and action.
No, they only have one Q table. They only have the Q table of the local this local state. Since if we choose the execution target, we can have the specific Q value for each device.
For each device, then they do the sorting for the global.
Yes.
Oh, okay. So when they update each device
the Q table.
Q table state. Okay.
Yes.
Okay.
Yes.
Okay. It still is kind of separate, you know, like
Yes, but I think in Dr. Wang Hao's paper for that Infocom paper, they still use the similar methods for the user selection. For that non-ID user selection paper, they use the similar methods. Yes.
But how can you say? Could you go to previous page for the reward function again? So energy locally, reward function, accuracy is the accuracy is energy global, energy local. How can you put the energy global and local somehow with the same scale? The reward function is for each device, or is for
each device?
For each device. Each device needs to learn that.
Yes.
And they adjust their policy, DVFS policy locally, right? But the server is going to select the user globally.
Yes.
Okay. How about okay, you can have the global energy. All right. Okay, if you're not selected, you don't take any action.
Yes.
If you're selected, you follow this this reward function, right?
Yes.
Yeah, you get the reward. All right. Okay, I just want to double check this. Okay.
Okay. So let's move to the their performance evaluation part. Firstly, let's look at the experimental methodology of their proposed algorithm. They consider each cloud federated learning system, which contains 200 of devices, where they have 30 high-end device, 70 mid-end device, and 100 low-end device. They emulate the federated learning system by this Amazon EC2 system. It is a virtually cloud computing platform. And so this is the setting of their system. And also they measure the energy consumption of the system by this, they measure the energy. For this energy measurement part, they use the monsoon power meter to measure the 3 devices. They measure the energy consumption of these 3 devices, which corresponds to a high-end device, a low-end device, and a mid-end device, respectively. And although they don't see the relationship between this EC2 system and these 3 devices, but I think they execute the federated learning training on the EC2 device and measure the energy consumption based on these 3 devices. And the computing capacity of these two devices should be matched. For example, the computing capacity of this high-end device M4 large should be similar to the computing capacity of this Mi Band Pro phone. So this is a system setting of their measure.
But here, I can understand they try to use the real device, the power data, to show, to mimic whatever they want to show on EC2, right?
Yes.
But is they match for this high-end device? For example, the Mi 8 Pro has 8 megabytes RAM.
They didn't provide such information, but I think they should be matched, or they will perform similarly. So I'm not sure, but because they didn't give the information of such devices.
Yeah, how can you say the G flops they match, right? And RAM match, even they match, how can you make sure the mechanism of EC2 generation, it's kind of consistent with the hardware board?
Yes, I still have the similar questions, but they didn't see the details of their system or the devices.
Yeah, I understand for EC2, is no way you can measure the power.
Yes.
But still, it looks weird, because if you want to work on the device, work on the device. If you want to work on the simulation instance, you work on the simulation instance, right? So how, I mean, the relationship is weird. It's kind of almost not that correlated. Yeah.
It's because it includes 200 devices, so it is impossible to run all of these devices with realistic mobile devices. So they use this platform to simulate that.
But you need to build up a solid connection between those, right? So you cannot say, okay, I classify them into 3 categories, then I use some real world 3 category, then I measure some of the power of them, then I say, okay, in my simulation, my high-end device have the same performance. That's not true.
Yes, I still have the question here.
Okay. Anyway, it's just accepted by micro, right? So, but I think that's one of the biggest concern. Also, when you do the DVFS, how can you say, I don't know, you do the DVFS on the local device, right? And you use those data.
Yes.
How much energy is saved to update your simulation, right?
Yes.
They work on the same frequency for the high-end device?
The frequency, I think we can adjust the frequency by this VF setting.
Yeah, how about for EC2? I'm not sure, because I'm not familiar with the EC2. For EC2, you can adjust CPU and GPU frequency?
Yes, I think they can adjust it.
Correspondingly, they try to build a match between those, right?
Yes.
Then for this one, I'm still not sure. For example, the first one, the second one, it seems their CPU frequency almost the same. Their GPU frequency is almost the same. So why you call it the Mi 8 is the high end and the Galaxy S10 is middle end, whatever. Medium, I would say.
Actually,
you don't know.
I don't know.
Also, their power consumption is similar, right?
Yes.
That should be true because their frequency kind of similar too.
Yes. Actually, I don't know the details of their settings, and also they don't show the details.
They don't show the detail. Yeah, but yes. If you call it one is the high end, one is the medium end, at least you show us something, you know, that really distinguishes them. For example, the memory, if Mi 8 has a lot of memory, Galaxy S10, not that much. But I think here the major thing they adjust is not memory, it's the GPU and CPU. But for GPU, CPU, they're similar.
Yes.
You cannot say, okay, Mi 8 is better company than Samsung. That's ridiculous. Anyway, okay. Yeah, please move on.
Yes, okay. And they run their works on 3 different data sets with 3 different models, and they initialize a synthetic code running app and emulate the random network bandwidth to simulate the runtime variance. And also they consider the data heterogeneity. They consider the different non-ID levels of their data distribution. Next.
Well, by the way,
okay.
Then could you? So yes. I mean, if they can do this, I think in the future we can do similar thing. We use the EC2 to do something for large scale network, but I think we can do small scale network locally with our, you know, Justin NVIDIA devices, and we can do large scale one use EC2 for the simulation or emulation. Also, for wireless bandwidth, you can, based on some local measured data, to say, okay, so I can assume, you know, those devices has a heterogeneous wireless transmission environment, something like that. Okay. Oh, what I mean is, in case you guys want to do large scale, I would say it's more like an emulation. It's not really experimental, or it's more than simulation. But I think that's a possible way.
Yes. Okay.
Okay.
Let's move on. The next is comparisons. They compare their algorithm with 5 baselines. The first one is a federated average, where they choose the action randomly. Is the C0 setting. They randomly select the number of high-end, mid-end, or low-end devices. And the second one is the power one, which means we aim at minimizing the power draw. So the C7 is the power setting, is the power method. And the third one is the performance, where we want to achieve the best execution performance. So the C1 is the performance one. And this all participant means they consider the heterogeneity and runtime variance for the participant selection, but they don't consider the target selection. So this is all participant. And for this AutoFL, it means we consider the execution target selection over this all participant method. The other say.
So here, I have another question. What do you mean by the minimize the minimum power draw? You choose C7. C7 is a low-end class, right?
Yes, that's why in this situation we can minimize the power draw. We have the smallest power of all the devices.
You mean the CPU and GPU, they running at a lower frequency? So their
Yes,
power
because
is
because it's a low-end device. So both the CPU or GPU, they consumes less power.
well, they play trick here. First of all, here they care about the energy, right? If you choose a low-end device, definitely the training time or whatever is going to be very, very large, very long, right? So overall, the energy definitely will be larger. The second thing, for the low-end device, for example, you use a second generation smartphone or something, right? You use a Nokia or something. It's not necessary, a power will be, there's a low power limit, that's for true.
Yeah.
But not necessarily the power should be less. It really depends on, the manufacturing techniques, right? So even some of them, I don't know, probably work at low frequency, the power can still be high. Yeah.
Yes, because I think here they want to consider some extreme case, because we don't know how to do this user selection. So they consider some random case and extreme case and compare it with itself. In the next few page, they will compare their performance with the existing approaches.
Okay, for the minimum power, from GPU and CPU point of view, probably that's true. But from the overall system point of view, it's not necessary. The lower frequency of GPU and CPU, the overall system power will be lower. Because it really depends on your board, your bus, memory access, it's the overall optimization.
Yes, I agree with you.
Right? Yeah, system, power optimization and designs. Okay, yeah.
Okay. And so for this OFL method, they say this is the optimal policy, but actually I don't know how to derive this optimal policy. I think this policy is similar to the method proposed in their paper. So I don't know you mean the differences between this optimal policy and their proposed policy. So next, let's move to the result overview. And these two figures show the average energy efficiency and the convergence speed of these 6 methods. And the first row is the convergence time speed up, and the second row is the PPW, which represents the energy efficiency. And from these 6 figures, we can find that the proposed AutoFL method obviously outperforms the federated average, the power and performance method, and for their proposed method, it performs similarly to the optimal one. And when we compare the all participant method and the proposed AutoFL method, we can find that from the energy efficiency perspective, their proposed method outperforms the all participant method. But if we look at the convergence speed, the all participant one outperforms the AutoFL one and the optimal one. The reason is that considering the execution target and the DVFS settings in AutoFL and OFL consumes more computing overhead, so it will converge a little bit slower than that of the all participant one. So this is the result overview. Next, let's see the adaptability to runtime variance, the on-device interference, and the unstable network. We have the similar performance evaluation results. The AutoFL one outperforms these 3 methods, and from the convergence time perspective, the all participant one outperforms the AutoFL and the OFL, and we have the similar results here. And next, let's move to the adaptation to data heterogeneity. we can find that if the non-IID level is high, all these three methods will not converge, and the proposed AutoFL method will learn the impact of data heterogeneity dynamically. Next, let's move to the another comparisons. They compare their methods with two existing approaches. The first one is FEDL. They adjust the local gradient updates based on the global weights. And the other one is the FedNova, where they normalize the local gradient from non-IID users to those from the ideal users. And all these two methods, they consider the heterogeneity, but they select the users randomly and ignore the execution target selection. And from these figures, we can find that the proposed one outperforms these three baselines, and especially for the energy efficiency, it can achieve nearly 50% and 40% higher energy efficiency compared with the FEDL and the FedNova. So that's the simulation results of their paper. And finally, I will conclude this paper. For this paper, they proposed AutoFL method, a reinforced learning based user selection and execution target selection approach for the federated learning training. And in their proposed approach, they consider all the system heterogeneity, the stochastic runtime variance, and the data heterogeneity during the training. And their method can significantly improve the energy efficiency and the convergence time compared with the existing approaches. And that's it. Thank you.
Any question from the audience?
Hey, Dan, I have some questions. The first one is, could you go to the motivation part? No, not the motivation. The motivation experiment part.
Motivation experiment. Okay.
Yeah, like they do three types of experiment as a motivation or something, right? So my question is,
here?
Yeah, here is a environment, and they do they test like three experiments. It's simulations. Next page. For impact of FL, global parameters, and characteristics, and also the NID and something, right?
Yes.
And
yes.
Yeah. My question is, why these kind of things motivate this paper to do reinforcement learning approaches, and how like any new insight or any new conclusion you don't know before?
Okay, so I mean, here is, for example, if we have one sighting, actually we don't know what's the optimal cluster of this sighting. We need to learn that, like here, yes, like here. So the optimal decision varies with lots of components, and it cannot be determined by some optimization method. So that's why we need the reinforcement learning to learn it. And also, for example, the device or data heterogeneity is changing over the time, because we consider some runtime variance, like I mean, like here, if we consider the runtime variance, maybe it's difficult to determine the optimal cluster. We can dynamically determine the optimal cluster if we use the reinforcement learning method. Maybe we can further improve this energy efficiency and the convergence speed.
Oh yeah, so the result you give me is just like
some
something
observation,
like random, but they have some rules, right?
Yes.
So it's not clear. So do this.
Yes.
You propose they propose methods.
Yes.
But I want to say like the conclusion here, on-device interference prefer to high-end devices, high commutation, and memory capabilities. Which like the conclusion is you can learn this from like the papers you read before, right? You can
yes,
intuitively guess, right?
we can know that, but actually we don't know the specific number of each type of devices. Actually,
you don't need to know actually, but you know how to explain like why like prefer high-end devices is better in some case, and why unstable network you should prefer low-end devices, something maybe, right? And so
we have some explanations on this selection. For example, for this on-device interference, the high-end device because the memory capacity or the computing capacity is high, so it can handle the interference, which means some other co-running apps may not have the large impact on the federated learning training. So that's why we need to choose the high-end device. We prefer the high-end device for this on-device interference setting.
I think
okay.
the one against the, I'm sorry to jump in. The one against a little bit against the intuition is the first one, right? I mean, if we allow DVFS, right? So as long as you work in the efficient way, even you have a high-end device, it's not necessary you use a very high GPU and CPU frequency, right? You know what I mean? That's you can lower your high-end device level to the medium or low. So if there is no running variance, I believe probably even from energy point power point of view or energy point of view, I think a high-end device can still be as good as the mix of high, middle, and low. Because it's not necessary you use that high frequency.
Yes, but I think for this paper is a 2-level or 3-level control problem. If you only consider the DVFS setting, I think it should be similar to that Mobicom or Mobisys paper. They use the reinforcement learning to adjust the DVFS.
What I'm arguing here is their motivation is not necessary to be accurate, right? So if you classify the task like this, no running variance on device, yeah, probably that's true. But say if you have some task, right, very CPU or GPU computing intensive, right? Your low end or middle end device cannot handle that. Still, I think the high end device works the best. You know, they give us some special case. In this runtime variance case, I believe those tasks is kind of mediocre, or it's kind of have a general requirements of those devices. You know, it's not like target
I
at
agree
high
with you.
CPU and GPU frequency, right? But that's one thing. The other thing is, like I said, if you allow for DVFS, high-end device theoretically can always be lowered down, leveled down to the medium end and low end. I don't think there is a specific reason, you know, even for the non-runtime variance case, even the task is kind of mediocre, is general to everybody. Still, the high-end device should be perform as good as the C2 and C3. You know what I mean? I think they play some special trick here. Say, okay, I use the default high-end device DVFS or whatever. I don't interfere with the DVFS, right? It doesn't matter what kind of task. I see for the high-end device, I keep a lower bound running frequency or something. The power is still high. You know what I mean?
Yes, I know. But I think for their paper, I think one of the motivation is that they want to have a general model. I mean, it can automatically select the actions, whether it is a high-end intensive model or low-end device intensive model. They want to generate a general policy to suit all of these settings. I think that's why they call it AutoFL. They want to automatically choose the selection without the expert experience.
Yeah, that means everything is by default, right? So you don't adjust anything or optimize anything.
Yeah, yes.
You just based on the stuff, then you select, right? Okay. I'm sorry for jumping in. Jiahao, please continue.
Okay. Okay. Let's go to another topic. So could we go to the experiment?
Okay.
Federated average part.
Next page or?
Yeah, next page maybe. Like here, like why they consider training accuracy? You see here some lot of training accuracy. How they get this training accuracy? Like under the same setting, different user selection, something like what's the control variable?
I think the accuracy is the model converge. For example, if we use the federated average, maybe we cannot run it to 99%. Maybe I guess. I'm not sure. This accuracy is the accuracy the model converge. And from this page, we can find that the proposed method, like the AutoFL, also their training accuracy is larger than the baselines. So
okay, I see. Okay. Another question is like like our group like do a lot of research on energy and on the communication efficiency part. Like there's a list of works, right? Also you do something and you do this test by something. What's like our method with this paper, which is better and why?
I think for our current paper, for our previous paper, we need to firstly calculate a convergence bound, and then we can have our optimization problem. But for this paper, I think they don't need such theoretical analysis. They just use the reinforcement learning to dynamically control the learning process. I think we are from the different perspective, and for our paper it's more theoretically, and for this paper it's more based on some observations and experience. Yes, and also they consider some non-ID issue or some variance, I think is a benefit of their paper.
I think for a race current paper, the ongoing paper probably
similar to this one,
but still different. I don't think they consider too much about the communication. Also, I think other, I'm not going to say other experiments is kind of emulation results, but all our results is based on the experiments. Also, I think our DVFS policy is not default one. It's more like, we design
adjustable one.
Yeah, adjustable, optimal DVFS policy. For local iteration number, we also try to, design that for follow certain kind of policy. But I agree with Dian, there's some factors we didn't consider that much in our current, even in Ray's ongoing current work. Like, I'm not sure, Ray, you can fix me. Like for the non-ID data, stuff like that. Also the waiting idle time, probably we ignore that. So there are differences. Also, this paper didn't trade off the communication and computing time actually, right? So they just do the selection. We are more from optimize the performance point of view, trade-off things. Yeah.
Okay.
Yeah. Yeah.
So do you think like our approach with this paper have different conclusions, like different motivation, different insight, like how do we choose parameters when we
No, I think we have a
run a model?
even the motivation were different. For this paper is like select, right? We select different things, different kind of users, stuff like that. For our paper, it's more like you trade off between the communication and computing. And for each of it, how can you minimize the energy consumption? Our motivation is kind of different, right? We will trade off communication and computing. They're kind of select everything, select the DVFS, select the users, you know. So we're different.
Okay, okay.
Yeah.
I see. So overall, like do you find or ask Dian something or Pat? So do you find any like interesting part like new things you don't know before, like from this paper, and like how do we choose the better sets when we train file learning? How do we choose the participation something? And also like can this reinforcement model can be easily transferred to another new environment something? That's it I want to ask.
Okay, so actually, for this paper, I think if you have read the Dr. Wang Hao's paper and that,
yeah, I have read that, and I think many papers related to reinforcement and further learning, they combine together. This is the first one, and or this is the first one paper.
I think for this paper, I think the method they use or the algorithm they use, I think is very similar to Dr. Wang's paper, and that Mobis's DVFS adjusting paper, adjust DVFS paper. I think their methods are similar, and I think for the new things we can get, I think maybe for some control variables, maybe we can consider the reinforced learning to choose that, not only based on the optimization method we use currently. I think we can consider some like the dynamic programming or reinforced learning method to solve some problems like the Ray is doing. We can include these components in our method.
Yeah, I think from my perspective, the major contribution is auto, right? Because if you consider previous file learning paper, they fix one or two things. They try to adjust another one or two, three things, something like that. In particular, for some theoretical paper, even for Dr. Hao Wang's paper, the same thing, right? You try to fix something, assumption, then you derive some good things. Even for experiment stuff, it's still fixed. Even for our own paper right now, we fix something, then we try to adjust the rest of it, right? This one is just like Dian mentioned, is automatically matched with any kind of problem setting, right? It can be transferred to any kind of environment. Technically, I don't think it's very new. DVFS is existing. You know, this deep reinforcement learning, guided file learning, many people talk about that. I don't think it's very new, but you know, like the micro and many Mobises, this kind of conferences, they really care about, okay, you can match for everyone first. Second thing is you can really work on the either real world emulation, simulator, emulator, or you can work on the real mobile device. You know, you can implement that, you can deploy that. I think that's a major thing.
Okay.
I think major contribution is auto. It can be fit for any kind of environments automatically. Yeah.
This is because reinforcement learning with the further learning.
Yes.
Or their system design.
And the system design, yes. Put everything together, yes. And implement that, deploy that, yeah, automatically. Yeah.
Oh, maybe that is their contribution. Right.
Yeah, that's a different from purely theoretical paper. I don't think theoretically they have any. Also, they didn't have any kind of theoretical conclusion, right? So it's different from the theoretical paper, though.
Okay. Thanks, Albert.
Yeah.